G'day everyone. Day 4, Magnetic Material Investigation Apparatus. So this is a quick little fixture that I built for studying magnetic materials in general, but in particular these EAS tags that we talked about in the previous video. It's basically a drive coil. So there's a central coil here with a lot of turns on it that produces a magnetic field to stimulate the material, and then we have a pair of opposed readout coils. So these are connected antiphase, such that I've sort of carefully adjusted their coupling to the drive coil such that they cancel most of the generated field. And so with nothing in the core, so we've got a hole here that we can put trial materials into. With nothing inside the core, there should be very little, if any, voltage induced in this winding, because these are connected in series, but antiphase. In the drive side, I've just got a shunt so that I can actually measure the current in here. I'm also measuring the applied voltage, but that's coming from a 50 ohm signal generator. So you've got an LR circuit there, so there's some phase shift. We'll ignore the complexities of the exact AC circuit that's happening here, but basically produce magnetic field in core, which is proportional to the current. Material does something to that, or does something to the material, and you can then read out the disturbance in the field without having to deal with the huge signal that would come from the drive waveform alone. So the drive waveform is cancelled in the readout apparatus. Electrically, it's really simple. It looks like this. Drive coil, readout coils, they're antiphase, so the voltage across here, almost all of the generated VD drive wave will be suppressed. On the oscilloscope, it looks a bit like this. So the blue rectangular pulse there is the synchronization output from the signal generator. So that's in phase with the voltage, the sine voltage that's coming out of the generator. The purple waveform is the voltage across the coil. So there's a slight phase shift there, which is caused by the LR circuit. The light blue, aqua, I guess you'd call it, teal, waveform is the current shunt voltage. So that's proportionally out of the current that's actually in the coil. And the yellow signal, which is mostly noise at the moment because it's cranked up, is the induced signal detected in the detection coils. So if we try a ferromagnetic material in the core, for example, just this piece of ferrite here, what will happen is you'll get a signal that's basically in phase with the drive waveform. So it's acting like a transformer. You're getting an induced signal, and it's mostly in phase. There's some phase shift, but that's a useful effect that if you really wanted to, you can recover the complex permeability of this core material. But for now, ferromagnetic materials make in-phase signals. If I apply it actually to so I'm applying this to one end where it's in phase. If I applied it to the other end, you'd see that you get an antiphase signal out, because you're just coupling into that antiphased side of the readout waveform, readout coil. Alternatively, if we say put something electrically conductive but non-ferromagnetic, like this piece of aluminium, it's my X-Acto knife handle, if we put that into the core, we'll get a signal that's shifted roughly 90 degrees, a quadrature signal. So what's actually happening is that the drive waveform is inducing eddy currents in the aluminium. So it doesn't have any ferromagnetic properties, but there are induced currents in the aluminium, and then that induced current is phase shifted because it's a dB/dt thing, and then that is producing a output in the pickup coil. So as you can see, if I continue to put it right through such that the eddy currents kind of cancel because they're being produced kind of evenly in both coils, I can push the aluminium through such that you eventually get something that looks more in phase. But the idea is to put the sample only into one one pickup coil, and really the rest of it here is just to buck the drive waveform. So, what do these things look like? What do these tags look like? This is an unperturbed tag. It hasn't been killed by degaussing that little bar magnet inside it that we talked about previously. So if I put this into the core, what we'll see, might have to actually turn the gain down a little bit, yeah, to get much of a, oops. Okay. You'll see that there's some distortion happening here, but the distortion's asymmetric. And that's that little DC bias magnet in there. If I flip the orientation of this around and I put it in the other way, then the asymmetry will be on the other side of the waveform, the rising versus falling side. So that's because basically the magnetic polarity of this, or the orientation of there's a definite direction of the magnetization. So in one half of the cycle, it's working with the bar magnet in here, or it's working against it. So what you've done is basically bias the BH curve of this material one way or the other, so that it's not symmetric about zero, symmetric H, about H. So if we take a degaussed core, which is this guy here that has a little cross on it, and we put the degaussed core in there, we'll see that it has pretty symmetric until it actually starts saturating, and then you can see the distortion is symmetric about the waveform's zero crossings. So that's because this is the little bar magnet in there is basically completely degaussed, and it's really not doing much at all in this experiment. It's just, it obviously has some permeability, but it has no remnants. And note that the drive amplitude here from my drive coil is not sufficient to coerce the bar magnet. So if I put the magnetized one back in, you can see that if you kind of advance it to the point where you're actually starting to saturate the opposite one, you'll see the nonlinearity there, but the asymmetry remains. So you've just kind of shifted the BH curve along a little bit. But you're not demagnetizing this. Like if the drive waveform was sufficient, it could actually coerce the little bar magnet as well. But right now, the drive level is low enough that we're just pushing around the met glass and not the permanent magnet inside these strips. If you put like a single strip in, you can get some interesting behavior. Like currently I'm running this at 1 kilohertz. This particular coil, unfortunately, the drive coils has a resonance before 58 kilohertz, so I'll have to build or rebuild a similar apparatus if I want to do like a frequency domain scan to look at the mechanical resonances of these strips. This particular apparatus is built for more, general use. It can also give you an idea of, well, there's a lot of things you can do with this apparatus, particularly if you use it with lock-in and get, really phased, resolved information out of it. But we'll probably talk about that later. But the strips are kind of interesting. You probably can't hear it, but I can hear it, and sometimes I can feel vibration from the strip. I'm guessing that's a magnetostrictive thing going on. But, yeah. It's currently making a noise. See the waveform too. Sometimes there's little oscillations on the wave, and I don't know if that's some kind of beating effect or what's going on. Definitely worthy of a little bit more sophisticated analysis once I make this to be something less than the lash up that it is at the moment. I also need more drive amplitude, I think, to be able to really saturate these cores. So I'll probably just shrink the apparatus in general to something that's obviously if the diameter is smaller, it's much easier to achieve the current and the magnetic field density in the core sufficient to really saturate and potentially even like saturate the bar magnets inside these, or coerce the bar magnets inside here. Anyway, yeah, that's about it for today. It's a pretty simple little apparatus. It's all 3D printed. I made a cute little stand for it, that it can kind of sit on. I should post the files, I guess, but these are all designed so they can be printed without support. They're actually made in 2 halves and they join together. The same with the internal spool, and there's this shield over the spool that lets these sit on it. And you can slide these backwards and forwards. They are glued in place. One of them's glued in place. The other one's free to move a little bit so that you can use it to really null that drive waveform. And there is some frequency dependence in exactly where that null position is. I'm not entirely sure what that is causing that. I'm guessing the drive coil might not be completely symmetric, and you get phase shift over the length of the winding as you approach resonance, because it's no longer strictly what you would call a lumped impedance. You've actually got the length of the wire is mattering then. Yeah. Anyway, enough for today. See you tomorrow.